In the last presentation, we introduced binary logic. The Boolean algebra used in this course works with binary variables and logic operations. It uses constant values of 0 and 1, uses capital letters for the variable names, and has three basic operations: and, or, and not. The Boolean function can be described by a Boolean equation consisting of a binary variable identifying the function followed by an equal sign and a Boolean expression. Single output Boolean function is a mapping from each of the possible combinations of input values to a result of 0 or 1 as an output. Multiple output allows those input combinations to be mapped to combinations of 0 or 1 on the function outputs. Power Windows was the Rush album that came out after Grace Under Pressure. It is also the primary example discussed in this section of the textbook, and they're a wonderful tool for getting your dog a burger from McDonald's. The equation you see here is a Boolean equation representing the electrical control for lowering a power window in a car. If L is equal to 1, then the window motor is powered up to turn in the direction that lowers the window. If L ends up equaling 0, then the window motor is not powered up. Let's look at the variables that make up this equation. D is an output produced by pressing a panel switch on the inside of the driver's side door. With D is equal to 1, we have requested lowering of the window. With D is equal to 0, we have not requested the lowering of the window. The next part of the equation is X. X is the output mechanism of a mechanical limit switch. If X is equal to 1, the window is fully down. If X is equal to 0, then the window is not fully down. Last but not least, A is the automatic lowering. A is a signal generated by timing logic from D and X. Whenever D has been 1 for at least 1/2 a second, A becomes 1 and remains at 1 until X is equal to 1. In other words, if the driver requests the window to be lowered for 1/2 a second or longer, the window gets lowered automatically to a fully down position. So, overall, L is equal to 1 if D and X not is equal to 1, or if A is equal to 1. Based on our work with the equation, we can create a truth table for our power window function. It's worth noting that while we can have multiple algebraic forms for a function, there's only one way to represent a Boolean function in a truth table. We can also draw up a logic circuit diagram for it based on the equations, as you can see on this slide. We can also transfer the circuit into either Verilog or VHDL. We'll introduce these two hardware definition languages a little bit later in this module, but this is what the model of the logic circuit would look like in Verilog. This table gives several important identities in Boolean algebra. It has two columns that illustrate the property of duality. Briefly, the dual of an algebraic expression is obtained by interchanging or and and operations and replacing ones with zeros and zeros with ones. If we take the dual of the expressions on both sides of an equation, we still have a valid equation. It's also important that any expression can be substituted in for x in this table. Final thing to note is that associative and commutative laws work the same as in ordinary algebra. One set of laws that may not be immediately obvious are DeMorgans Laws. The negation of x or y is not x and not y. Likewise, the negation of x and y is not x or not y. As you work with these laws, they will become more apparent. You can also extend DeMorgans Laws to take on more variables. You can also see the order of operations illustrated in this table, particularly in part B. Not is first, followed by and or comes last. Boolean algebra is also useful for simplifying circuits. In this figure, we have the original expression on the top, but we can simplify the expression through Boolean algebra identities. Page 51 of the text shows the algebraic simplification in this example. You can also write up a truth table to show that these two expressions are equivalent, and as you can see, the circuit in the lower part is much simpler and much less cost than the one on top. When a Boolean equation is implemented with logic gates, each term requires a gate, and each variable within the term designates an input to a gate. A literal is a single variable within a term that may or may not be complemented. To reduce costs and to optimize, it's beneficial to reduce the number of terms and the number of literals. The consensus theorem shows that the third term is redundant and can be eliminated. The dual of the consensus theorem is also important. Both the original and the dual can be applied to simplify complicated Boolean equations. To get the complement of a function, you can negate the entire function and apply DeMorgans Laws. It's a bit easier to take the dual of the function equation and complement each loop. There are a couple examples of both techniques on pages 54 and 55 of the text. Thanks as always for watching. I'm sorry that Boolean Algebra doesn't lend itself to a lot of animation or a lot of colors. We'll discuss standard forms next. In the meantime, make sure to check Lima for assignments, announcements, and more.